Hi, my name is Xiliang Diao. Today I want to introduce my proposal about defining the Mississippi River plume with numerical drifters. River plume is the mixing region between seawater and fresh water. A lot of different properties inside and outside river plume that researchers want to study. For example, the strong submeso scale eddies inside the Mississippi River plume. Figure 1 shows the sea surface salinity. Blue represents the fresh water and yellow represents seawater. We can see the Mississippi River plume's huge impact and a lot of small eddy features inside the river plume. However, how to quantitatively define the Mississippi River plume is still a problem. Here we want to use some numerical drifters statistical metric to quantitatively define the Mississippi River plume boundary. Here is our figure 2 shows our numerical drifters model. Green represents the drifter's salinity is less than 33, and the eddy there shows a complexity and small scale features. Purple represents the drifter's salinity is bigger than 33, and the eddy there show large scale and more uniformly featured. So these two areas eddy features are very different. And then in turbulence theory, in the energy spectrum, Y is the energy and X is a wave number. Wave number has a unit of 1 divided by distance. So left is a bigger distance, right is a smaller distance. And the energy injected location is the most dominant eddy's radius because they have the highest energy. When the energy injected into the system, they will cascade to two directions. To the larger distance, it will mainly through energy cascade, and the slope will be -5 divided by 3, and the relative dispersion will show power law relationship. While to smaller distance, it will mainly through the entropy cascade, and the slope will be -3, and the relative dispersion will show exponential relationship. And if a drifter's inertial distance is less than the dominant eddy's radius, when they separate and the distance is increasing, they will experience these two different patterns. Lucas did some drifter experiment in the Gulf, and his statistical result is like this. In the left finger, X represents time, Y represents distance squared, and Y is in log scale. So a straight line here represents the exponential relationship. In the right finger, both the X and Y are all in log scale. So a straight line here represents the power law relationship. So Lucas' conclusion is in the Gulf, the relative dispersion will show exponential relationship below 50 kilometers and will show power law relationship above 50 kilometers. And recall this theory, so the energy injected location is 50 kilometers. When pairs distance is increasing, it explains these two different patterns. Based on all this theory, I raise my first question. So what is the difference of the relative dispersion drifter that always inside and always outside the river plume? And can these different values be used to define the Mississippi River plume boundary? My hypothesis is inside the river plume, due to the high freshwater discharge, the submeso scale eddy field are very strong. So the drifter pairs will separate more faster than the outside river plume. So if a boundary can be found to separate these two eddy fields very accurately, then their relative dispersion difference should have the biggest different value. My method is first I use trackpad model to set the numerical drifters and use the ROMS model to provide the background speed field, and then I choose a isoplane and to select the drifters. Figure 5 shows the red represents the drifter pairs that are always less than 33, and blue represents the drifters that are always bigger than 33. And in the small box, solid line represents the drifters' relative dispersion, while dashed line represents drifters' numbers. And then I calculated the drifters' relative dispersion. Green represents the dispersion inside the real plume, and purple represents the relative dispersion outside real plume. And then I calculated these two lines' difference. Finally, try different isohelans, try different slanted lines, and find out the biggest difference value. We think the isohelan with the biggest different values should be the most reasonable choice for the Mississippi River plume boundary. My second question is, what's the slope? What's the slope of the relative dispersion of drifters that always inside the river plume and always outside the river plume? My hypothesis is inside the river plume, due to the eddy radius is smaller, so it will be more, the slope is more like a exponential relationship, while outside the river plume, the relationship should be more like a power law relationship. Our analysis method will be very similar to Lockhart's analysis. And my third question is how different the relative dispersion of drifters will behave in different seasons. Because the submesoceal eddies is mostly induced by the strong freshwater discharge, so we propose season would be a very important factor, especially for the drifters that are always inside the Mississippi River plume.